I'm back, everybody. This is lecture number 1, installment 3. And last time, you might remember, I left you hanging in midair. I didn't mean to do that. But we had two independent solutions, e to the negative 2x and e to the negative x. They were both solutions of the complementary equation phi of dy equals 0. And I said that any linear combination of these two things is also going to be a solution to the complementary equation. And this is, in fact, the general complementary solution. Well, maybe I need to put up or shut up. Let's show that this linear combination of e to the negative 2x and e to the negative x is a solution. C1 and C2 can be any constants. Now what we're going to do is compute v prime and v double prime. So let's see, derivative of C1 e to the negative 2x, derivative of the exponent is negative 2 times C1 e to the negative 2x. Derivative of e to the negative x is, well, the derivative of the exponent is negative 1 times c2 e to the negative x. And v double prime, derivative of negative 2x is negative 2, so negative 2 times negative 2 is 4, c1 e to the negative 2x. Derivative of e to the negative 2x, derivative of e to the negative x. Derivative of the exponent is negative 1 times this negative 1 is positive 1. C2 e to the negative x. Okay. Here is v prime, and v double prime. And I'm going to plug these into the expression y double prime plus 3y prime plus 2y. I'm going to plug in v for y. I'm going to plug in v prime for y prime. I'm going to plug in v double prime for y double prime. And let's see, instead of y double prime plus 3y prime plus 2y, I've got v double prime plus 3v prime plus 2v. And here's my v double prime. Here's my 3v prime. Here's my 2v. I'm sorry. Yes, 2v right here. Now let's collect common terms. I have 4c1 e to the negative 2x. 3 times negative 2c1 is negative 6c1 e to the negative 2x. And I've got 2c1 e to the negative 2x, 2c1 e to the negative 2x. Okay. Now what about my e to the x's? I've got c2 e to the negative x. And I've got 3 times negative c2 e to the negative x, so that's 3 times negative c2 is negative 3c2 e to the negative x. And I've got 2c2 e to the negative x. Well, what happens here? 4c1 plus 2c1 is 6c1 minus 6c1 is 0. c2 plus 2c2 is 3c2. Minus 3c2 is 0. Okay, this whole right side is 0. So it really is true that v double prime plus 3v prime plus 2v is 0. In other words, v of x, which is c1 e to the negative 2x plus c2 e to the x, this is the general complementary solution. Now, the previous observations and example lead us to a method for finding the general complementary solution. Finding the general complementary solution, the solution of phi of dy equals 0. First step, rewrite the equation using operator notation in the form of phi of dy equals 0. Based on this, step 2, construct the auxiliary equation phi of m equals 0. And that's easy because the polynomials phi of d and phi of m are the same polynomial. They're just written in terms of different variables, that's all. So from this we get the polynomial, and we write the polynomial in terms of m, and that's our auxiliary equation. Step 3, solve the auxiliary equation for m. Now, if m is an nth degree polynomial, there should be n roots or solutions. So the n distinct solutions, m1, m2, mn, to the auxiliary equation yield n independent solutions. E to the m1x, e to the m2x, e to the m sub nx. So these are all independent solutions to the complementary equation phi of dy equals 0. Now here's the punchline. The general complementary solution is the set of all linear combinations of these n independent solutions. So C1 times this thing, C2 times that thing, plus plus Cn times that thing. So the sum of these things with arbitrary constants is the linear combination of all of these independent solutions, and this is our general complementary solution. General complementary solution, there it is right there. And I say we illustrate with an example, or maybe two examples. I think 2 is good. Okay, first up, find the general complementary solution to the equation y double prime minus 9y equals negative 4x squared minus 2x plus 14. Well, the corresponding complementary equation is just this equation with the right side set to 0. So that's the corresponding complementary equation. Step 1. Rewrite the equation using operator notation in the form of phi of dy equals 0. So, y double prime minus 9y equals 0, same as d squared y minus 9y equals 0, same as the polynomial d squared minus 9 times y equals 0. So this is our complementary equation using operator notation, and look at that polynomial phi of d, or phi of d. Based on this, we construct the auxiliary equation. Same polynomial phi, just different variable, m. So phi of d is d squared minus 9. Phi of m is m squared minus 9. So our auxiliary equation is m squared minus 9 equals 0, where this is phi of m. Step 3, solve the auxiliary equation for m. M squared minus 9 equals 0. Okay, that's m plus 3, m minus 3 equals 0. So our solutions are m1 equals negative 3 and m2 equals positive 3. And remember, the distinct roots to the auxiliary equation yield n independent solutions. E to the m1x, e to the m2x, e to the mnx, to the complementary equation phi of dy equals 0. I don't like the way that looks there. Phi of dy equals 0. Well, we have two independent solutions, e to the m1x, where m1 equals negative 3, and e to the m2x, where m2 is positive 3. So e to the negative 3x and e to the 3x are our independent solutions for the complementary equation. The general complementary solution is the set of all linear combinations of these n independent solutions. So in other words, just multiply that by an arbitrary constant, multiply that by an arbitrary constant, and add them together. Here's our arbitrary linear combination of the two independent solutions. And this is the general complementary solution. Now, I said we were going to do another example, and I think we should. Yeah, this one will have a little bit of a twist to it. Find the general complementary solution to the equation y double prime minus 2y prime equals negative sine x minus 2 cosine of x. First, note that the corresponding complementary equation, well, how do we get that? We take the original equation and set the right-hand side to 0. So the complementary equation is y double prime minus 2y equals 0. Step 1, rewrite the equation using operator notation so that it's in the form of phi of dy equals 0. Y double prime minus 2y prime equals 0, same as d squared y minus 2dy equals 0. And if we factor out the y, d squared minus 2dy equals 0. This is our complementary equation, and there's the polynomial phi of d squared minus 2d. Based on this, we'll construct the auxiliary equation phi of m equals 0. And remember, phi of d and phi of m, they're the same polynomial, just in terms of different variables. Phi of d is d squared minus 2d. So phi of m is m squared minus 2m. And our auxiliary equation is phi of m equals 0, or m squared minus 2m equals 0. So step 3, solve the auxiliary equation for m. So m squared minus 2m is 0. We have a common factor of m there, don't we? So factor out the m. And our solutions are m sub 1 equals 0 and m sub 2 equals 2. The distinct roots or solutions to the auxiliary equation yield independent solutions, e to the m1x and e to the m2x. Our independent solutions to the complementary equation are e to the m1x, which is e to the 0x. See, e to the 0x is just e to the 0. That just equals 1. So first independent solution is 1, okay. The second independent solution, e to the m2x, is e to the 2x. So 1 and e to the 2x are our two independent solutions. The general complementary solution is the set of all linear combinations of these independent solutions. So in other words, we take an arbitrary constant c1 and multiply that by the first solution. Take an arbitrary constant c2 and multiply it by the second solution. And this is our general complementary solution, c1 plus c2 e to the 2x. Now, what does that really mean? It means that if we look at the original equation, the original complementary equation, phi of dy equals 0, or if we go back just a little bit further, the original complementary equation right here, every solution of this complementary equation looks like this. It looks like some constant plus some constant times e to the 2x. Okay? That's it for the first lecture. Let's do homework exercises on page 175 also. A exercises numbers 1 and 2. And in about 2 days I'll have lecture number 2 out, now that I got the hang of doing this. It's good to be back. Oh, by the way, when you're going through these notes, it might be a good idea, or when you're going through these lectures, it might be a good idea to take some notes while you're doing it and hit the pause button every now and then to write some things down, just to make sure that you're really getting it. And if you have any questions, email me, and I will try to get back to you promptly. For now, goodbye.